Okay, so we know that sampling distribution of mean values for random samples can be very well described by a normal distribution. And the standard deviation for these values for the statistics is called standard error, and it can be calculated. It depends on two things. It's the standard deviation of your values of your population and the sample size. So that's how we calculate the standard error. The problem with this is that we need to know sigma. We need to know standard deviation for the population, which usually we never know. Okay, so if sample size is large, then the standard deviation of your sample, it can be a quite good estimate for the standard deviation of your population. And in this case, you can substitute this formula to a s over square root of n, where s is your sample standard deviations. But what to do if sample size is small? Okay, the problem is follows. Look. Imagine that this is your population. Okay, in this case, it's normally distributed population. This is the true average of your population, and then the spread of the values depends on the standard deviation. Okay. Now let's say your sample size is 4. If you take 4 random values, let's say they will look like this. If the smaller sample size is, the more chance will be that the spread of these values will be smaller than the whole spread of your population. So it means that standard deviation of your sample, if sample size is small, will be much smaller than standard deviation of your population. And that leads us to underestimation of the uncertainty. So our confidence intervals will be smaller than they should be, and therefore the true population average will not be inside for many cases. Okay, so that's the problem. How to solve it? Well, use another distribution, which is called student's t-distribution. There was an engineer, William Seeley Gossett, who worked on Guinness. His main task was to optimize beer brewing processes, and in this case, of course, large sample size is very expensive. So he investigated how the behavior of small sample size. He investigated the behavior of statistics for the small samples, and then he found out a distribution that describes this behavior quite well. He published his papers, scientific papers, using a nickname student. So therefore, the distribution actually is called student's t-distribution. Okay, so let me show you a couple of slides. So the idea is following. First of all, this distribution looks very close to normal. Okay, but if normal distribution, the spread of normal distribution, its shape depends on the standard deviation. For the t-distribution, it depends on two things: standard deviation and degrees of freedom. And if we fix standard deviation, if we assume that standard deviation is equal to 1, and average is equal to 0, so we standardize the distributions, then this is how it will look like. On all these plots, the blue line is a normal distribution. Okay, for example, you can see here we will have -2 and 2, and then it means that we have 95.5% all values in between, right? But the red curve, if you look at the red curve, it's a student's t-distribution depending on the sample size. In this case, the sample size is 2, and you can see that the red curve is much more flat. So it means we should go much far from the average than just -2 to get the same percent of the values in between. Okay. Then instead of sample size, we use another statistic, which is degrees of freedom. You remember that in this case, the degrees of freedom is just n-1. So n-1, because we need to calculate the variance. And when we calculate variance, we lose 1 degree of freedom when we calculate average using the same values, right? So if degrees of freedom is 1, this is very flat. If degrees of freedom is 2, it means that sample size is 3. You see, this is the new line, this is the new line, this one. And this is the previous one that we have just seen here, okay? So you can see that it gets a little bit closer to standard, to the normal distribution. And then if you decrease sample size to 4, it gets even closer, even closer, even closer. This is, for example, sample size is 31. And you see it's very close to the red curve and blue curve are very close to each other, but still there is a difference, okay? How this difference influences the confidence intervals? Well, let's look at this plot, okay? I have 4 different distributions here. The blue curve shows the normal distribution. The green curve shows the t-distribution for sample size 3. The orange curve shows the t-distribution for sample size 5, and then for sample size 10, it's a red curve. Okay, so you can see how these curves relate to each other. Okay, if you look at these lines, and these ones, this is 95% interval of the values. Okay, so you can see that for normal distribution, you have around plus minus 2. So this is plus 196, right? And this is minus 196. So that's what we know already. Okay, so if you want to get 95% of the values inside, you should go 196 standard deviations from mean. Okay. Now, if you don't use normal distribution, if you use t-distribution, then this range will depend on your sample size. For example, if sample size is 10, it's this one. So you can see that it's slightly larger than if you use normal distribution. So it's a compensation for a smaller sample size and for not knowing the true sigma. Okay. Then if your sample size is, for example, 5, this one, you see it's even larger. So it's about 2. I don't remember exactly. I think it's 2.5 or 2.8. Then if your sample size is only 3, you see it's much larger. It's plus 4.3 here and minus 4.3 here. Okay. So it's twice larger than if you use normal distribution. So that's the concept. So if you use t-distribution, it's very close to normal, but it has a compensation for a small sample size. The smaller sample size is, the bigger uncertainty will be. Okay, so if you want to be more certain, take bigger sample size. If you can't, then use uncertainty that t-distribution gives you. Okay, so that's the case. So if you have a big sample size, you can use normal distribution. If you use small sample size, you can use t-distribution. In fact, this 500, it's a stupid rule. You will see later, a little bit later, why I use this 500. In fact, you always just use t-distribution, because if your sample size is large, t-distribution will be the same as normal distribution, so it gives no difference at all. Okay. Let's see at this some t-values. Okay, so this is how many standard errors we should go from the average to get a certain number of values in between. Okay, so this is the table of t-values for 95% confidence. Okay, look, if these numbers are degrees of freedom. Okay, so the sample size is plus 1. Okay, look, if you have only 2 values in your sample, well, first of all, never do that for two values, but still, if you have only 2 values, you should go 12.7 standard errors or standard deviations from the mean. Okay, 12 instead of 196. But if you have at least 3, then it's already 4.3. Still large value, but not 12. And then if you have, for example, 10, it looks pretty reasonable. It's 2.23. So it means that it's not that far from 196. Okay, so that's very important, and it shows you how your uncertainty can be better and better and better just by increasing a sample size. Better in this case means smaller, right? So the confidence interval will be smaller. Okay. Then if you have 30, look, it's just two standard deviations. Then if you have 100, it's 1.98. Now the reason I told you I used this 500 values was that for 500 values this t-value is about 196 something 3 or something. So it's very close to 196. But in fact, you will get exactly 196 only if you have a very large sample. In theory, it's infinite. Okay. Now, how to get these t-values? Of course, you can use the these tables with the values, but it's not very efficient. You can use R for that. Okay. So I'll remind you quickly the basic idea. Let's say we have standardized distribution. This is the distribution. Okay. And then you want to have 95% values, right? So you need to find these two tails. You have 2.5 here. Then you have 2.5 here. But you remember that we always, and then this is t and this is minus t, it's symmetric. We always, when we talk about probabilities, we always mean probability to find a value below given, right? So for this value, probability to find a value below this, it's 0.975, right? And for this value, the probability to find below this is 0.025. You can use each or either of these with ICDF function. That will actually give us the proper t-value. But if you use this one, it will be negative. If you use this one, it will be positive. Okay. So that's what I'm using here. So you can see that I got t-value using ICDF function. It's a co-function in R. This is my probability, and these are degrees of freedom. Okay. Then for 99%, you remember if you have 99% in between, it means you have 0.5% here, 0.5% here. Then you have 0.5% here. I will not make the curve. Okay, so again, you have this t value here and minus t value here, minus t and t. Okay, so again, probability for this t value will be probability to find the value below this 0.995, and therefore we just use it here, and this is degrees of freedom. Okay, so n is a sample size. Yeah, now there is one more limitation actually. If you want to use t-distribution and sample size is small, then you need population to be normally distributed. So if your sample size is 3, 4, 5 values and population is distributed normally, you can make a normality test, for example, and then you can use t-distribution, no problem. But if your sample size is not normally, your sample is not normally distributed, you can use still the t-distribution, but only if sample size is larger than equal or larger than 30. Otherwise, it's a limitation. Otherwise, you can't do that. Okay. So now we know a solution. Let me show you some examples how to calculate the confidence intervals.